So we're talking about file systems and how disks work, if you remember. So I think I forgot my sample disk I brought in my office. That's okay, I will just use some figures on the board to explain. This is the picture to keep in mind that I put up last time. Disks or hard disks basically have this thing called platters. There are more than one. Platter looks like a CD or a DVD. I'm sure all of you have seen what that is. And data is recorded on these platters in concentric circles. So you basically have a circle that's referred to as a track, and each tracks are partitioned into sectors, and that's where data is stored. Okay? The way you read or write to a disk is you have something called a disk head that moves back and forth. The disk itself, the platters are spinning, okay? And the disk head is going to basically be stationed onto a particular track on a particular circle, and then it can read whatever data is going by underneath that disk head. Okay, so the way typically you would like to read a sector is you first move the disk head to the right track. That's referred to as a seek. So if you want to read the outermost sector, the track or the disk head would have to move from this track all the way back. And then once it's positioned on the right track, you have to wait until the right sector spins by under the disk head, and then you can start reading or writing. So typically any disk I/O involves a latency to position the disk head on the right data, on the right sector rather. Okay, and there are two kinds of latencies you incur. One is the seek time to position the head over the right track, or the tracks are also referred to as cylinders. The other one is rotational latency, which is the time for the sector to rotate and spin by under the head. And then once though that latency has been incurred, only then you can do I/O. Okay? So what we are actually going to do, okay, for the rest of the class and maybe even next class is to understand how to implement file systems, okay, from two perspectives. How to lay out the data on disk, where do you put the files, okay, so as to reduce this overhead. Okay, so because this is all wasted time as far as the disk is concerned. It's not doing anything useful, it's just trying to move the disk head and put it at the right location so something useful can happen, so you can do reading and writing. So we'll look at how do you lay out files on disk to reduce this overhead, and then we'll also look at how do you read data. Once you have stored it on disk, how do you read data and also try to reduce that overhead. So we'll look at it from two perspectives. A layout of files on disk, actually reading and writing once you laid out the files on disk. And all of the discussion will focus on how are you going to optimize this overhead, reduce it as much as possible. Okay. Here's a slightly more detailed picture of a hard disk. Okay, the disk I brought last time actually looks like this inside. So there are multiple platters. Each of this looks like a CD with a recording surface. There are multiple platters that are stacked. Okay. Each platter has a disk head, okay, that you can read or write. Now the way the disk works is only one of these disk heads can be active at any time. Okay. You cannot, although these are independent disk heads, reading or writing independent platters, you can have only one of them active. So what you typically do is you pick the platter number. Okay, so you can say go to platter 3, go to track 17, read sector 25. This is how requests will come in, and the right disk head will activate. It will move to the right track, okay, and then it will read or write the specified sector. Okay, this is typically how disks are going to work, and all of this time these things are spinning. Okay, so they are going to basically spin. The disk head simply moves back and forth. It doesn't move anywhere else. All it is doing is it can move forward or it can move backward, okay, and then it will position itself on the right track. Okay, so that's the picture to keep in mind. Any questions on this before I talk about file system layer? Okay. Now the other thing to keep in mind is all of the optimizations that we are going to talk about today, okay, may not be necessary if you have solid state disks. Okay, solid state disks don't look anything like this. SSDs as they are called, they look like main memory. Okay, there's no moving parts. Disk is simply laid out as a collection of blocks that can be independently accessed, and you just go to that address and pull out the data that's stored there. Okay, so there is no latency. In this case, if you are reading disk I, block I, and you want to read block J, which may be on some other track, you are going to incur a seek and a rotational latency. In SSDs, none of that is true, because all you say now read the location J. It's like you go to memory location J and pull out the data. The same thing is true of disk. You go to disk location J, which is block J, and just read or write that data. Okay? So SSDs don't need to perform some of the optimizations that we are going to talk about now. Okay? Now, since these kinds of drives are still quite common, less so in laptops, but in server devices and other PCs, you still get these kinds of disk drives. These optimizations are still necessary in today's OSs. Maybe 5 years from now, this technology will become obsolete, and all of the optimizations that we are going to talk about will also be obsolete, and you will have to redesign the file system to optimize it for SSDs. Okay, different considerations come into play there. We are not going to talk about SSD file systems in this class. It's more advanced topic. We are only going to talk about very basic file system designs, assuming traditional magnetic hard disks. Clear? Okay. So this is what we need to keep in mind. Okay, so as I said, you have basically a file ID and a block number within the file, that is the data you want to read or write. What we will do is that we will map that into a platter number, a cylinder or a track number, and a sector number. Okay? And then once you're done this mapping, you are going to go and read or write that specified sector. And these are the things we need to keep in mind. We need to support efficient, sequential, as well as random access. Okay? I mentioned last time that files you can access sequentially. You can open a file and read it from beginning to the end in sequence, or you can randomly jump to arbitrary locations in the file and read it. That's what databases do. You say go read a record, it will go and pull the data from the right location in the database file. Okay? Now file accesses could be sequential or random. Okay? So we need to design our file system to support both of these types of accesses efficiently. And we'll see that in some cases, some structures are more efficient at one of the axes than the other. Okay? So we'll ask the question, what kind of structures will you use? How will we lay out the files on disk to support those accesses? Okay? So all of those questions will relate to sequential and random access. Okay? Now as far as this mapping is concerned, we are going to do something very straightforward. What we will do is the following. Okay, so we'll assume that you have a platter. For now, just assume the disk has only one platter. It doesn't matter. If it has more, you'll simply generalize this. Okay, so it has these tracks. Each track has a certain number of sectors. So we will assume that each track has equal number of sectors. Let's say each track has n sectors. Okay. And we'll simply number the sectors in increasing order. Okay, so this is 1, 2, 3, 4, 5. So you have 5 sectors here. Then you go to the next track and say 6, 7, 8, 9, 10. Then you say 11, 12, 13, 14, 15, 16, 17, and so on. So you are just going to take all the sectors and you are going to number them from the innermost track to the outermost track, or vice versa, in increasing order. So every sector gets a unique integer ID. Okay, so all you need to do is, if you want block B, you are going to do essentially B over n and get the track number, and B mod n to get the sector on that track. Okay, so this is how you are going to convert a block number to a platter number. Then I just showed you for a single platter how to get the track number and the sector number. You can do the same thing for platters. We'll assume each platter stores an equal number of blocks. So you first figure out which platter is the block on, and then which track and which sector on that track. Okay? That mapping is straightforward. Yes, question?
So a block is a part of the sector.
Okay. That's a good point. So I've been using the term block and sectors. Okay? Now, for the purposes of this class, we will assume that one block is one sector. Okay? That is not necessarily true. A block is a file system concept, abstraction. It's a chunk of data that the file system deals with. A sector is a hardware concept. It's a granularity of data that you can read or write from a disk. Okay? Typically, the values of a block is typically some multiples of sectors. Okay? Typically, sector may be 512 bytes. Most disks use a 512 byte sector. Okay? file system blocks can be anywhere from 1 kilobyte to 4 kilobytes in size. Okay? That means that typically a file system block may have 2 sectors, 2 consecutive sectors, or up to 8 consecutive sectors. A block is a consecutive set of sectors. Okay? Here, for simplicity, we'll assume one block is equal to one sector, just for simplicity. But in general, when you format your file system, you specify the block size. Okay? Typically, a file system can be formatted with any block size you specify. It may have a default, okay? But you can change it. And when you do that, you will basically use some number of sectors to be within each block. Yes.
Are blocks generally assumed to be in the same track?
Are the blocks assumed to be on the same track? Typically, what you do is you assume that a block is contiguous on a track. Okay? Now, if you pick some vague block sizes, the file system may have to do extra work because you may not have an integral number of tracks fitting onto a sector. A block may overflow. How to deal with that is up to the file system. Okay, in most cases, the way you choose it, if you choose it to be 1K or 4K, it will work because there are some number of sectors that some multiple of 2 blocks are some multiples of number of sectors, and it just works out. But it doesn't have to be. Okay, but in most cases, it is. Yes.
Why would you choose like a bigger, small block size? What are the benefits of one or the other?
Okay, that's a good point. So, point is, why would you choose a larger block size? What is the benefit of it, right? So, the advantage actually comes solely from trying to reduce this overhead. Okay. Now, if let's say you pick 512 byte blocks, okay, as we will see shortly, when you lay out a file, the blocks don't have to be next to one another. They can be scattered across this to reduce fragmentation. Now, if you want to then read 1 kilobyte of data, if you have 512 byte sectors, you have to read 2 blocks. Okay? The 2 blocks can be scattered, so you'll incur 2 seek, 2 rotational latencies. Okay? So you'll slow it down. If you had a block size of 1 kilobyte, that entire chunk of 1 KB may be stored in one location, so you'll only incur 1 seek. Okay? So larger block size are simply used to reduce the seek overhead. Okay? In SSDs, this would not matter at all. Okay? Because you would basically, there's no overhead whether you choose a small block size or large block size, you incur a constant time overhead to go and read some chunk of it. Here it matters quite a bit. Okay? So the idea is to choose as large a block size as possible to reduce the seek and the rotational latency overhead. Now you will ask, why not make it 1 megabyte? Why did you stop at 4 kilobytes? Okay, and the answer is it depends on what sizes files are. Most files that you have in a system tend to be actually very small, okay, a few kilobytes. If you choose very large block sizes, you will have internal fragmentation because you cannot allocate a chunk of data that's any smaller than 1 block. So if you have 1 byte file, you're still going to allocate 4 kilobytes if that's your block size and waste the rest of the space. Okay, so choosing a block size is an important consideration. It's something I was going to come to later, but since these questions came up, it's important to understand why you need to make some of these decisions. Any other questions here? Okay. Yes, there's a question.
It's kind of off topic, but if you have multiple platters and you have data that has to get split up or it's not occurring on the same platter or something, would be ideal to take stuff off of one platter to make room so that everything fits on one?
Okay, so question is, if you have multiple platters, does it make sense to do some defragmentation so all of the data fits on? So when we talk about random access, you will see what considerations come into play. The question, you don't even have to think of it as multiple platters. You could have asked the same thing about tracks. Do you want to keep all of your data together or should it be scattered across tracks so there will be more seeks? Okay? And the answer is there is going to be a balance between performance and issues like fragmentation. The more data you store together, the more fragmentation issues you may get and the less efficient you can make use of space, but you will lose in terms of performance. Okay? So you have to balance these two, yes, to the extent possible. And we'll talk about that in just a few minutes. Okay, so before we start looking at real disk layout, let's look at a few sort of higher level detail. Okay, the first thing we will keep in mind is for every file that the file system is going to keep on its disk, it will keep some additional metadata information in a structure called the file descriptor. Okay? So the file contains data. The file descriptor contains information about the file. Who is the owner of the file? What's the current size of the file? where on disk are the blocks of the file stored. All of this is what we refer to as metadata. It's data about the data. That's what metadata is meant. And so you'll have a file descriptor and store all of that information, and then you will have the file itself, which will have the data. So you always, for a file, any file, you have two pieces of information the file system has to keep. The data itself, which may be spread across multiple blocks, and the file descriptor, which is data or metadata about this file. Okay? So we'll have to think about what kind of structures to use for file descriptors as well as we go along. Okay? Now with that in mind, here are a few things to keep in mind. Okay? If you look at any typical disk, okay? Take a PC or a laptop and look at its disk. Okay? Look at all the files that are stored on that disk. And if you analyze the files, you'll roughly see these observations hold true. Okay? First observation is most files are small in size. Okay? The median size of a file is 1 to 2 kilobytes. Okay? That's the median size. So most files are very, very small. Okay? Okay? At the same time, most of the disk space is taken by a small number of very large files. Okay? So we have lots of little files, but if you look at where does all the space go, it goes into some small number of large files. Maybe you stored a movie, maybe you took a lot of pictures. Each of those files are larger, but there are not a whole lot of them as compared to all the other files on your system. So you just list all the files and look at the sizes of files, you'll see most of them are small. There are small number of gigantic files and they take up most of the space on the disk. Okay? And then I/O operations typically target either small or large files. So you want access to either large or small files to be efficient. Okay? So we'll use this observation as we go along. Okay? So first, and how we will use it is as follows. Number one, you want to try to optimize for the common case. When you design any system, you always ask what's the common case. The common case better be fast. If the common case is slow, then your entire system will be slow. So if most files are small, you want your file system performance to be good for the common case, which is so small. At the same time, because a lot of disk space is taken by large files, you still want somewhat efficient access to this gigantic file. You don't want to tremendously slow it down. You may be willing to pay a small cost, but not a huge cost. Okay, so those are observations that we will take and try to design some file structures. Okay, so what that says is per file cost must be low, and then large files must have good performance. Okay, so we'll start from very straightforward policies. Okay, so this is very similar to what we did in memory management. Okay, when I talked about it, I said when we come to disks and files, we'll come back to the same set of considerations. Okay? So the first file layout is contiguous allocation. Whenever you have to store a file, allocate data for it contiguously on chunk. Okay? So if you create a file, okay, you may just say it is 3 sectors long, so I'm just going to allocate it contiguously here. Okay, these are the 3 sectors. Okay, you want another file with 10 sectors, you just pick maybe one track and another track next to it, something like that. Okay, so you're going to allocate data contiguously on disk. The OS is going to maintain a list of free disk blocks. Okay, these are blocks that have not yet been allocated to a file. Whenever you need to go and allocate data to a file, you find a chunk of blocks, which is a hole. Okay, same concept as a memory hole. A chunk of blocks that are contiguous that can hold the entire file. Okay, if you do this in your file descriptor, in your metadata, all you need to do is store the start location, the start block number, and the size. Okay, the start location is here. Okay. So you just say the file starts at this block number and it's 3 blocks long or 3 sectors long. So you'll just go here and you know where the entire file is stored. So your file descriptor is trivial. All it is storing is the start location of the file or disk and the size, because it's stored contiguously. Once you get to the start of the file, you know where the entire file is stored on this. And nothing more needs to be stored. Okay. Now, there are some advantages and disadvantages, obviously. The advantage is this is the most straightforward, simplest structure that you can come up with. Okay. It's efficient both for small and large files, okay, because basically once you get to a particular location, okay, once you go to start location, that's one seek and one rotational latency, and then you just read contiguously from that point on. So sequential access will take one seek and one rotational latency, okay, because you just seek to the beginning of the file and just read the file from that point on, and the diskette is already positioned there. Random access is also fine because you can simply compute. If you know where the first location of the file is, if you want to go to the 5th block, you'll just basically go 5 blocks down from there. You know that. You can simply compute it and go read that block. Okay. So both sequential random access work well in this case. Yeah, so simple structure, but and also efficient. Okay. Disadvantages are also probably clear. Okay, first is what happens if the file size changes over time. You open some file, okay, you write some more data and you save it. The file has grown in size. Okay. Now if there isn't space at the end here, some other file has been stored there, you'll have to move that file somewhere else because that's the only way to store it continuously. Okay. So changing file sizes is a problem when you have contiguous allocation. And over time, as files are created and deleted, realize that you will delete files if you're done with them, and you create new files all the time. So if you delete this file, these 3 blocks become free. Okay, now you created a whole. So over time, the same things that were true in contiguous memory allocations are true here. Your disk will get fragmented. Okay, you will have lots of holes. You may have lots of space in the aggregate, but no hole large enough to store a gigantic file. So you have to defragment your disk and so on. If you ever run any defragment tools, this is what it is doing. It's moving things around to create larger contiguous free blocks. Okay, so these are advantages and disadvantages of this approach. Now, very early versions of operating systems used contiguous allocation, okay, because it was the simplest layout. Okay. Except one scenario where it is still used today. Okay. Contiguous allocation is typically not used for file allocation. Okay. Can you think of any scenario where this still makes sense to use today? Yes.
The write once disks.
Okay. So if you have CDs or DVDs where you just write data once and only thing you can do after write is read it afterwards, it makes perfect sense to use contiguous allocation. Okay? Because none of these two things are true. Okay? Once you burn a CD or a DVD, file sizes won't change because you can't write to it again, and there is no fragmentation because you can't delete data. Okay? So both of those limitations go away once you have written to a DVD. Okay? So in that case, you're better off going with contiguous allocation because, as we said, it's simple and it's very efficient. Okay, so any file system that you see on a CD-ROM drive or a DVD-ROM drive uses contiguous allocation. Okay, because you just create the file system once, you burn it, and you're done. Okay, so there are other kinds of write once disks, but those are the most common ones. Yes.
So wait, then does the disk itself actually control how it allocates space, or does the OS that's writing to the disk tell it where we're going to put it?
So the question is the disk allocate space or the OS? Typically the OS is the one that's going to allocate space. The disk doesn't do anything. All that the disk does is it receives requests to read, saying go read I, block I, and go and fetch block I, or write something to block I. That's all that a disk will do.
Okay.
That's what an IO device is. So all of this space management is done by the file system in the OS. Okay? Now, when you're writing to a DVD, in this case, it will be basically used the DVD burner software will lay out the files and then you'll just burn it.
Okay.
Right? So it's not the file system. In that case, it's the burning software.
Okay.
It'll take the files, it'll lay it out, make an image, and then just burn it onto
Okay.
DVD. Okay, but all of that is done not at the hardware level. It's done in software. Any other questions here? Okay. Next layout. Linked lists. Okay, so we are going to make files that look like linked lists. Okay? Here's an example of a file. So in this case, as you can imagine, we are going to go away from contiguous allocation. We are going to say put blocks wherever you want on disk. They can be scattered anywhere, and we are going to chain them together. Okay? And the structure we are going to use is a linked list allocation. So this is your file descriptor. Okay, this is where you store, this is the name of the file, this is the size of the file, this is the owner of the file, and so on. And one more entry in the file descriptor is a pointer to the beginning of the disk. The pointer is simply an address saying the first block. So this is what is in the pointer, saying the first block is platter 4, cylinder 20, sector 5. Okay. So that's basically a pointer to the first data block of the file. Okay. So in this block, which may be, let's say, a sector, okay, we are going to store some data, but the last byte or 2 bytes we'll have reserved for the next pointer. Okay. So if it's a 512 byte sector, let's say 509 bytes are going to be data, and the last 3 bytes will store these 3 integers. As an example, saying the next block is platter 2 cylinder 7 sector 1, and so on and so forth. Okay, so it's basically going to be a linked list, and every time you create a file, this is what you're going to create. You're going to allocate a file descriptor, and you're going to start picking vacant blocks on disks, okay, empty blocks, and start allocating it to file and chain them together in a linked list. Okay, this linked list is stored on disk. It's not a memory structure. That's something you need to keep in mind. So the pointers really are addresses of the next block, which is basically a platter number, a cylinder number, and a sector number. Okay. Early versions of FAT file systems used linked list allocation. There are FAT file systems that still use some form of linked list allocation. Okay. Now the interesting thing is all the free blocks on your disk can also be stored as one gigantic linked list. Okay. So free blocks, think of it as a special file where every block that's unallocated is also stored on that linked list. Okay, so in that linked list, you will not have any data stored in that free block. It will be some garbage, but each block will point to the next block on the list. Okay, now if you need to allocate a block, you just go to the head of the list, you pick a block and you give it to whatever file is requested, more space. Okay, is that clear? So fragmentation is gone, because you're not storing, so block 1 may be here, block 2 may be somewhere else, block 3 somewhere else, just simply chaining them together. Okay, so you simply put a pointer from one block to the next block. Okay, that's at the end of each block, you'll reserve a little bit of disk space and put that address. Okay, so this is what a file, FAT-like file system actually uses to store files. So advantages: fragmentation gone, contiguous allocation. Every sector can be used. It can be just allocated to some block. Okay. What about file size changes? Can we change the size of a file after it's created? Okay, you should be. Okay, so if you want to grow it at the end, okay, you'll simply allocate a new block, okay, and then you'll basically start writing to that block and put a pointer. You can even insert data in the middle of the file. Okay, so suppose you have some source code and you wrote some text in the middle, your file is grown in the middle. You can even do that if you want by simply inserting a block. It's a linked list. Okay, so you can insert a block, have this block point to that block and that block. You can do any of these things. The file can grow at the end, the middle, any of those locations. Okay, now let's talk about accesses. Okay, so we are going to worry about sequential access and random access. Okay. So let's ask how expensive is it to sequentially read the block from beginning to end? Yes. Okay. Can you? Okay, you have to read every single one, but what is it in terms of latency? You had something to add?
Well, there's just it can just read sequentially and go from one to the next to the next.
Yes. Okay, so this is linked list. Okay, so the way you are going to read the file is you go read the file descriptor first, read the head. Okay, look at this address, issue an IO request, and go read that sector. Okay, that will read the disk. You'll read that sector. Okay, you look at the end, saying what's the next block. You see the address there. Issue a request to the disk, saying go read that sector. Disk will read that sector for you, and so on. Okay. Yes.
You don't have to actually read the data, right? You know where the sector ends, and you can just skip that to the next one.
You do have to read the entire. So the minimum granularity of data is the sector. Okay. And since we are doing sequential access, the assumption is whatever application is requested, it wants the entire file. Let's say you open the file in your editor. You have a source code file. You open it for editing. The entire data, all of the code is read into the buffer of the editor. So you are essentially going and reading this chunk, this chunk, this chunk, and sticking it into your editor. So you are going to read the whole file. Okay. But as I was saying, the way you would do it is you will read it one block at a time. Once you read that block, you look at the address that's at the end, read the next block, and so on and so forth. until you read all of the data in the file. Okay. Now that sounds like that's how you traverse a linked list, but remember that this is happening on disk. Okay. As you read each block and issue a request for the next block, okay, the next block may not be contiguous, it may be at some other random location on disk. So each block here is going to incur one seek and one rotational latency access. Okay, even though you are reading this sequentially, right, you are going to incur n seeks and n rotational latency overheads to read n blocks. In contiguous allocation, you simply had to move the disk head to that location and then you could read the entire file in one shot. It was all stored together. Here you can only read one block, then you have to move somewhere else, read the other block, move somewhere else, read the other block. So you are moving the disk head back and forth because this data is not stored contiguously. Okay, so even sequential access, okay, is going to incur n seeks and n rotational latency. Okay. And random access, as you can imagine, you say go get the 10th block, requires you to traverse the linked list. There is no way to figure out what the address of the 10th block is without traversing the list, going to the 9th block and looking at that field and looking for the 10th block. Okay. So random access is essentially a linear scan through the linked list. It's not efficient. If you have a 4 GB file, you are out of luck. You have to read 4 GB to get to the last block because you don't know where the last block is unless you traverse the linked list. Okay. So sequential access, n seeks. Random access depends on where in the file you are going to read, linear scan. Okay, also n seeks. Okay, to read the nth block, or I seeks to read the ith block because you are going to actually go through. So random access is definitely not efficient. There's no way to just go and read some block. You have to scan through the entire prefix of the file to get there. Right? Sequential access you are anyway reading, so all the work that you're doing is useful because the application asks for that data. So you are willing to incur those n6 because you need the data anyway. In random access, you are going to just simply read the file, the early part of the file for just to get to the right location. Okay, so does not support random access very well. Number of seeks we already talked about. Okay. As I already said, FAT file systems, MS-DOS still use this. If you have USB drives that are formatted using early versions of FAT file system, they will still use similar types of allocation. Okay. Is that clear? So we looked at two that are very simple. Now we are going to try to look at two more slightly more sophisticated structures. Okay. The first one is what we'll call an index structure. Okay. So in the index structure, the file descriptor looks like this. Okay. It has some initial information such as owner of the file and so on, and then it has an array of block addresses, array of block pointers. Okay. And the ith block, okay, has an address. To get to the ith block, the address of that block is stored in the file descriptor. Okay. So just to draw a picture here. So that's your file descriptor. Let's say that's your disk. So the first block is here, second block. Okay, again, allocation is not contiguous. So you can allocate any block you want, but rather than chaining the blocks in a linked list format, you are going to keep an array of pointers in the file descriptor. And this array is going to have the addresses. So rather than putting the address at the end of the previous block, you're going to put the address in a different data structure, which is the file descriptor itself. So when you open the file, you'll read the file descriptor, you'll get the addresses of all the blocks in the file. When to go to the ith block, you look up the ith entry of the file descriptor, it gives you the address of whatever that block is, you go there and read it. Okay, so this is basically that file descriptor. Okay, it's an indexed structure where this file descriptor has an index to every block of the file. Okay, blocks don't need to be stored contiguously. Okay, so there's no fragmentation again. Is that clear? So now think about some advantages, disadvantages, performance, and so on. Okay, the first question you have to ask is, how large should the file descriptor be? So how large should it be for any given file? Yes. Okay. So you need at least as many entries here as the number of blocks. If the file has 10 blocks, you need 10 entries. If the file has 1000 blocks, you need 1000 entries. If it has 10,000 blocks, you need 10,000 entries, and so on. Okay, so the answer is the file descriptor needs to be at least as long as the number of blocks in the file. Is that clear? So then you should ask, how does the OS know when the file is created, how large to make it? Okay, let's say you create a file. You open an empty file, let's say, to write some Java code in it. Okay. The OS doesn't know, are you going to write 10 lines of code, 1000 lines of code, 1 million lines of code in just one file. It doesn't know. Okay. But when you create the file, this descriptor has to be allocated. This data structure is created at file creation time. Every time you create a new file, you have to go and allocate this data structure. Okay. The blocks of the file are allocated as the file is actually being created. But this data structure is allocated at file creation time. Okay, typically, the OS will not know how large the file is. In fact, the file may grow over time, over a period of days, weeks, months. It may keep growing. So when you created the file, the OS has no way of knowing how many blocks the user or whatever program created the file has intends to put in that file. So it doesn't know how large to make that data structure. So the only way around it is to say, let's assume that the maximum file size you have in your system is 1 gigabyte. I'm just making up a number. So if you say this file system supports files that are as large as 1 or 2 gigabytes, okay, then every data structure will have enough entries to basically keep 2 gigabytes of data in that file. Okay, so you pre-allocate a structure that's as large as the maximum file size you support. And then you don't worry, because then you have enough blocks. In most cases, many of those blocks will not be used. Only the first few entries will be used. The rest of the file descriptor will go unused. Yes?
Why can't you create a smaller file descriptor, and then if it gets filled, then create a new file descriptor and copy the elements over?
Okay, so the question is, why can you not create a file descriptor that grows with the file size? So I think the next data structure will be essentially that. Okay? This one is a single level index. There is no way. Think of this as an array. Okay? So the array is contiguous. It has to be declared when you create the file. That's the way the data structure is. Okay? There is no way to grow this array the way we have laid it up. We would like to extend this data structure so it can grow with the files. Okay? But that is not what this structure will do for us. Okay? So this, as I said, the only other solution is you create a data structure that's as large as the largest size and largest file size you support, and that's it. So then you don't need to worry about file growing. The problem though is that since we said most files are small, you created gigantic file descriptors to store up to 2 gigabyte files, and most of your files are 1 or 2 kilobytes inside. They have only one block in most cases. Okay, so 99% of your files will basically have lots of wasted space in their file descriptor, because you said I'm going to allocate the file descriptor assuming the worst case, that this file could be as large as the max file size. Okay, so not very efficient use of your file data structure. So either you have to ask the user to tell you how large the file is going to be, and you allocate a structure. How does the user know? When you write a Java code, do you know how large your file is going to be? Can you tell the system this file will be 732 bytes when I'm done? I don't think anybody knows, right? So you can't tell the OS. So if you can't tell the OS has to provision for the worst case. Yes. Yeah. You don't know, right? So OS doesn't know. The users clearly don't know. Users don't even think of file size. They just open files and do whatever they want. You hardly think of how large the file is. Ever. Right, so OS is stuck. Okay, so it has to. The only way to make this feasible is to allocate for the worst case and waste a lot of space, okay, which we will not like, because it's just not efficient. Okay, so not much wasted space for files, but a lot of wasted space for file descriptors if you provision for the worst case. Okay. Now it should be clear that both sequential and random access is easy. Okay. Sequential access, you simply read the file descriptor, look at the first entry, go fetch the block, look at the second entry, fetch the block, third entry, fetch the block. Each of those entries will be at random locations on disk. Each of them will incur a disk seek. Okay. Because all you will do is you'll go look at, so you read this structure into memory, and now you have all the addresses. Go look at the first address, say go get that. So that will go be a seek to that location. And then you go to the next one, and maybe another seek to some other location. Okay. So sequential access will still incur n seeks, like before. And that's okay, because you are reading all of the blocks. Okay, but now random access has become more efficient, because if you want to go read the ith block, you just go and look at the ith entry, and just go fetch that block. Okay, in the linked list, you have to go scan all the blocks. Here, you don't need to do that. You're actually going to the file descriptor and just indexing into the ith block and simply getting it. Okay, so you really have two IOs to get to the ith block. One IO to read the file descriptor from disk, okay, and the second IO to go look at this address and go read that address from disk. Okay, so any block, any location in your file, you can read with two disk accesses. One to read the file descriptor, the other to read the block once you get the address of the block from the file descriptor. That clear? Any questions on sequential random accesses? Okay, so disadvantages are you may have to set a maximum file size. That's dependent on the size of the file descriptor. Okay. So lots of seek because data is not contiguous, well, it's less efficient in terms of sequential access than contiguous allocation. Contiguous allocation is the best you can do as far as sequential accesses are concerned, because all the data is stored contiguously. And no other system can do better, but it has lots of disadvantages. Every other structure that we will look at will be actually less efficient than contiguous allocation as far as sequential accesses are concerned. Okay, random access is the same thing. Okay, so the last structure that we'll talk about is basically this generalization that I was just mentioning. This is what is used in most Unix-like file systems. Okay, so this is a multi-level index structure. Okay, so as the name may suggest, your index structure has actually multiple levels, and the index structure is going to grow with the file. Okay, you are not going to presuppose how large the file is. The user doesn't have to specify. File can grow or shrink depending on whatever the user is doing. The structure will also grow and shrink. Okay, and the structure is basically as follows. So this structure is also referred to in Unix terminology as an inode, an index node. Okay. So the last time when I was showing you file IDs, I did ls-i, and I showed you that every file has a name and a number. That number is the number of the inode. Okay, basically, when you create a file system, you create empty inodes, and they are simply numbered 1 through n. Okay, so there is some maximum limit on the number of files you can store. That depends on how many file descriptors or inodes are pre-allocated. And the ith entry is simply the ith inode. Okay, so when you create a file, you grab an empty file descriptor, that's the ID of the file. That's basically the inode number. Okay, that's why it says ls-i. I stands for inode. It simply is reading the ID of this descriptor. Okay, that's the ID of the file itself. And now let me tell you what this descriptor does. This descriptor, as is shown here, has basically one sector or one block, not even one sector actually, some fixed number of bytes, and it has 14 entries. Okay, basically you can store 14 addresses as is shown here. Okay. So the first 12 addresses are referred to as direct block pointers. Okay. So what that means is they actually directly point to data blocks. Okay. So until the file grows to 12 blocks in size, okay, you will use the first 12 entries and they will simply point to disk blocks the same way this index structure here was pointing to disk blocks. Okay. First 12 entries, direct block pointers. Okay. Now if the file grows beyond the 12th block at any point after it's created and spills over into a 13th block, then you have, or you use the 13th entry there and that entry is going to point to another block, okay, which is part of the file descriptor. This is not a data block. Okay, this is also an index file, and it's a one-level indirect block, a first-level indirect block. So this entry will point to the index file. Each entry here is actually going to point to a disk block. Okay. Now in this case, it says that each of this one has enough space for 1024 pointers. Okay, so you can basically grow the file by another 1024 blocks until you need to do anything else for the file descriptor. Okay. First 12 blocks go here. The next 1024 blocks go here. Okay, the pointers are here. Okay, so that's 1036 blocks. Now, if you grow beyond 1036 block, you will use the last entry there. Last entry is a double indirect. Okay? So you will allocate a disk block which will hold 1024 entries like this. But each of those 1024 entries don't point to disk block themselves, they point to other index blocks. And these index blocks themselves point to disk blocks. And so what you will do is, when you spill over into a 1037th block, you will allocate one of these and you will allocate one of these. That will give you space for another 1024 blocks. Once you use that up, you will use the second entry here and allocate another of these. And that will give you space for another 1024 blocks and so on until you used up all the 1024 entries. At that point, you have basically maxed out your file system size. Okay. Modern file systems will actually have a third entry here for triple indirect. Okay, and have 3 levels of indirection. Okay, yes.
Why there are exactly 14 block pointers?
Why are there 14 block pointers? That is how the system has been constructed. Okay, so first 12 entries are direct block pointers. Next entry is 1 level indirect. Next level is 2 level indirect. And I said modern file versions will add a 15th entry. So there are 15, not 14. That will add a 13th, third level of indirection. So you're asking why the number 12 or
Yeah, is it like who specified like the number? Just the
some file system designer thought of this scheme. It could have been 10, it could have been 12. They just assumed based on some analysis of how disks files are laid out that that's the number that makes sense. Okay, it's completely empirical depending on what common file sizes you see in typical disks. Okay, that's your question.
Oh no, I was just being
Yeah. Yes.
How many IOs would it take to find the pointer?
Okay. How many IOs would it take to find a pointer? We are going to analyze performance in just 1 second. Okay, if there are other questions on this structure before we talk about performance, let's hear them first. Yes.
So say like maybe in the second level, how does it know which index file to go to for a particular like data, chunk of data? Like how does it know how to go through? Or does it have to go through each one?
Okay. So let's walk through how the file system is going to go and get some block I. Okay, so code is going to work as follows. So you say open this file foo and read block I. Okay, this is random access as you can imagine because I block could be anything. Okay, so you'll go read the file descriptor first. Okay, and then you have 14 addresses. Okay, you'll say what is I? If I has range sort of 1 to 12, okay, you will say basically just look at the ith entry here and you're done. Okay, I is greater than 12. Okay, you say what is I? So if I is between 13 and 1024, okay, you say that's going to be in the first indirect block. So the way you will do it is you look at the 13th entry. That will be a block address. Okay, that will point to this block. You'll go and read this block from disk. Okay, that will give you the next 1024 addresses. Okay, and then whatever I is, let's say I is 100. You'll basically look at the 88th block here. Because there are 12 here and 88 there, that's 100. So you look at the 88th entry, that will be a disk block pointer, you'll go read that. Okay. If I that you specified is greater than 1024, okay, what you will do is you will basically read the last entry here. Okay. That will point to this disk block. That's the first level indirect. Okay. Then you will ask, okay, of that, where is it here? Okay, because you have to say if it's the first 1024 after this, it's here. This next 1024, it's the second entry and so on. So you'll index, you'll find that block and that will point you toward this block. So that's basically the code that the file system will have to implement to get any block I. Okay, yes.
So you can assume that the numbers are the same for every multi-level index.
What numbers meaning what?
You'll always have 14 block pointers. 13 will go to.
Yeah, so it's either 14 or 15 in typical Unix file system. Like this is what Unix does actually. So if you use this type of inode, yes, it will have 15 entries. Most cases 15, 14 was sort of the old generations of this file system, and they'll have direct block pointer, single, double, triple indirect. Okay. Now it should be clear that this structure is pre-allocated. There are only either 14 or 15 entries. That is going to constrain the maximum file size this file system will support. Okay. So you can analyze what's the maximum number of disk blocks and the file size you can support here. Yes.
Can the index file contain index to pointer to, or is only contain data?
Can the index file contain what?
Index to pointer to.
The index file typically has pointers to other blocks. These blocks will actually contain the data.
Yeah, but can it also contain like pointer to other index file?
Can the index file contain pointers? No, this is what is a single file representation. Right? Each file has an index file that allows you to get to its data blocks. Okay, so index files don't point to other index files. Index file point to index blocks with for that file. Okay, this is an index block, that's an index block, that's an index block. Okay, it's not going to point to another. So if there's another file, it will have the same structure for it. Okay, so here you have the file name, all of that, and then the block pointers. Yes.
When I is equal to 14, would it go to the 13 pointer and then go to the 1024 and read the first one, or would it directly go to 14?
I is 14, so remember you count from 0, but let's assume you count from 1. So if I is 14, that's the 14th block, okay, not the 15th. Technically it would be the 15th block, but let's assume it's the 14th block. So you look at the first 12 here, okay, it's not here. So it will be basically, you'll read this and then you'll read the second block here. You won't read the data. This is also an index block, so you can read whatever you want here. And you don't read things sequentially. You simply say, I need the 14th address, where is it? So you say it's the second address of that block. So you go there and read the second address, you're done. You're not scanning the data itself, you're just simply going and indexing into the index structure. Yes?
You can find the file descriptor from the index file.
You can find the file descriptor.
Point the file descriptor from the index file.
You're asking where is the file descriptor?
And looking at another pointer to the file descriptor from the index file.
This is the index file.
Yeah.
We are using the term file descriptor and index file synonymously. So your question is, how do you find the file descriptor? How do you find this? Is that the question? Okay.
Inside the another file.
Okay, so if you are asking where do you find this to begin with, right? So you say open file foo, first you have to go and locate the file descriptor. And you are asking where do you find that? Is that the question? Okay, so typically that depends, that goes into the structure of a file system. A file system has typically what are called blocks and super blocks. Okay? All the file descriptors are stored in super blocks, and super blocks are in well-known locations. So when you create your file system, when you format, this is what it is doing. It's going and allocating reserving some space to keep the super block. File descriptors, which is this part of the file descriptor, is pre-allocated. They're empty, but they're pre-allocated there. Okay, you don't go and just create some block and create a file descriptor. You basically created a whole bunch of empty file descriptors. That's what's happening when you format a file system. Okay? So when you create a file, you simply go pick an empty one, okay, and you use it. And they are actually stored contiguously. So if you want the ith file, okay, remember I said files are numbered. They have names, but they actually are numbered. What you're simply going and doing is in the super block, you're reading the ith file descriptor, and they are stored contiguously. So there is no intelligence, you need to say where is the block file descriptor. You say what's the number of the file. If it's file 100, go read the 100 descriptor in the super block, and you're done. Okay. That answer your question? Okay. So coming back to the question I had asked, which is if you have 14 pointers, okay, I said that caps the size of the file. There's a maximum limit on the size of the file because there are only so many addresses you can store based on those 14 pointers. Okay, so let's try to see what is the maximum size of the file. Okay, so you have 12 blocks which are here. Okay. This doesn't work. And then the next first level indirect gives you space for 1024. What about the next one? How many addresses does this store?
14.
This one. That's 14. This
Yeah.
is an entire block.
Oh, is it 1024?
So it has 1020. This has 1024, but it's pointing to other blocks.
So 1024 squared.
Okay, so it's 1024 square. Okay. This is the number of blocks this descriptor can store. That's the maximum file size. If your file size grows beyond that, you say exceeded maximum file size. This times the block size is the maximum size of the file in bytes. Okay. Now if you have 15th entry, okay, that will be 1024 cube because that's triple indirect times the blocks. Okay, now this is a very large value. Okay, and these blocks are allocated on demand, so you only put them in when the file grows to that size. So this is a fairly large size. Okay, so typically it will be as large as your disk itself if you do the computation. Yes.
But that entire thing isn't allocated as soon. Like you don't make this entire structure on disk as soon as the file is created.
When the file is created, you just allocate 14 pointers.
Okay.
That's it. All these additional pointers are only created if the file grows beyond the 12th block and only as required. So if you go to a 13th block, you only do this, etc. Okay, so the structure is going to grow with the file. So it's very space efficient. Unlike the single level index where you have to allocate a very large array, here you are allocating a multi-level index completely on demand. Okay, yes.
But if we have something that goes over 1036 and a little over 1036, so wouldn't all the space for pointers to index files be wasted?
So let's say you do for 12 blocks, you're done here. You do another 1024 blocks, you use this up. If you overflow, you will allocate the last entry here, that will create this block. Okay? You will only allocate one entry of that and create this block. This is not yet created. So you allocated 2 blocks, that will give you another 1024. If it grows beyond 1024, you allocate a second entry here that points to another block. So you allocate blocks of 1024 that can hold 1024 additional blocks for the file at a time. Okay, so you are not, just because you went into second level indirect, you didn't allocate them all. You only allocated this, and these things are allocated on demand. Okay, so you will not go and allocate these many index blocks. You will only allocate 2, and a third one, and a fourth one. Only when you grow, the file fills up, will you have actually 1024 square. Yeah, so it is doing things completely on demand. You only allocate what you need to and no more. Okay, so advantages, disadvantages. It's just simple to implement. It's not quite true. It's not that simple, but it is a multi-level index. Okay, so that's what it is. It supports incremental file growth. We already talked about this. Okay, it is very efficient for small files. Okay, small files will have a few blocks. Just have a descriptor with entries to a few blocks and you're done. You will basically just access the file descriptor, and whether it's sequential or random, you're going to just read all those blocks or just index some ith block and go read it. Okay, I said optimize for the common case. The common case is small files. In small files, both sequential and random access is efficiently supported just by reading the file descriptor. And then you just go and read the block. Okay. Now, you progressively penalize the file as it grows bigger and bigger. Right? Because if you have very large files, you may have up to 3 disk accesses to randomly seek to a location. Okay, so you read the file descriptor, one disk I, one seek, one rotational rating. Let's say you're reading somewhere at the end of the file, you go look at a double indirect block. Okay, so that's another disk I. Okay. That may point to one more disk block. You have a third disk I. That is the one that points to the disk block. That's the fourth disk I. So for large files, they pay a higher tax. Okay? And that's okay because that's not the common case. There are a few of them. And 4 disk blocks is still not bad. Okay? You think of a linked list where you may have to scan 1,000 IOs to get to the 1,000 block. Here, it's at most 4. Okay? Still bounded. Yes.
Well, if you have to read the whole thing sequentially, would it be faster to just sweep through all the index files, find all the contiguous blocks, done all in memory, and then go through and do all the IOs and chunks?
Okay. The question is, if you want to read it sequentially, you would read the index block. Okay. The probability of whether blocks will be contiguous or not really depends on how full or empty the disk is. If the disk is mostly empty, these blocks, although they don't need to be contiguous, can be kept contiguously and you will have good performance. If the disk is full and highly fragmented, you will not get good performance. So it really depends on what is on disk. It is mostly empty, mostly filled, highly fragmented. That's what performance will depend on. Nothing to do with the file system, it's what's the state of the disk. Yes, question.
If we have a lot of small files like that go just above the 12 pointer blocks, we're going to create fragmentation because there are 10, 24 data blocks that we're assigning.
Okay, so you're asking would it create, so these don't have to be contiguous, these are pointers. So you have to realize that nothing here is contiguous, right? So this is your file descriptor, this is the single level indirect, this is your disk, this can point to one block, this can point to some other block on some other track, this can point to some third block. So this is not at all contiguous allocation. This is a file descriptor, this is an index. Okay, so here the addresses are stored one after another, but the addresses are not contiguous. Addresses could point to any block. This could be block 10, block 100, block 50. So you are not basically restricting anything from being contiguous. Okay, so small files, good accesses. Okay, there is a small optimization that is even done. Your file is really tiny. If it is like a few bytes, not even a few kilobytes. Okay, at least in the Unix file system, that entire data is actually stored in the file descriptor itself. Okay, why allocate one block of 4 kilobytes and write 1 byte to it? You can actually, here you have 13 bytes. Okay, so you can actually write that file in there itself. So for very tiny files, you want additional optimization. It's only done in Linux, not a typical optimization. Typically, you would have to allocate at least one block and use few bytes of that block. Okay, but in either case, small files are well treated because they only use indirect blocks. As the file grows progressively larger, okay, you pay progressively higher cost. Okay, and that's okay. Your very large files, you don't penalize all the small files for it. Only that access to that file pays that additional overhead of 2 to 4 disk accesses to get to any blocks. Okay? You have to realize that random access is efficient in that you will have at most 3 to 4 disk block accesses to get to any block, okay, depending on where in the file you are trying to access. First 12, your random access is only 2 blocks. Okay? The next 1024, 3 IOs, okay, and so on. Okay, so it's bounded. It's not the same as multi-level single level index, but it's bounded. Okay? And yes, unlike contiguous allocation, you'll have more seeks. Even sequential access will mean n seeks at least. Okay? We said file size is bounded, okay? And there's a question there, what could the OS do to get more contiguous access? Okay, although it's not required that file data be stored contiguously, if you have a completely empty disk, why not store the file contiguously to the extent possible? And if it grows, then some other blocks can be stored elsewhere. But by and large, if you try to cluster blocks together, you will have fewer seeks in practice. So these are optimizations, they are not requirements. So if you have a largely empty disk, the OS will try to store the blocks together. Why just scatter the blocks around when you could allocate them contiguously? If the file grows, then so be it. Some other blocks can be stored elsewhere. But the first few blocks did get stored together. Okay, so these kinds of optimizations will help you get more contiguous access. That clear? Okay, you could of course run a defragmenter which actually tries to take all the blocks that are scattered together and put them together. Very slow, very expensive process. Typically you don't want to do it. You want to just do whatever the OS has already, go with what the OS has already done. Okay, so as I said, this structure appeared in a very old version now of Unix 4.3. It's widely used in all flavors of Unix. Unix or Linux or any of these OSs. Okay. Last point here is going to be on free space management. Okay. And this is simply the problem of how does the OS track what blocks are allocated to files, what blocks are free, unallocated. So if you create a new file, you can allocate blocks to it. The way you do this is either you have to keep what is called a free block list or a bitmap. A bitmap is simply a structure which has one bit for every sector on your disk. And if the bit is 0, that means it's not in use. If the bit is 1, that means it's actually taken. So whenever you allocate blocks to a file, you basically change the bitmap and put a 1 for that sector you just allocated. When you delete files, okay, you don't actually go remove any data. You leave the data as is, but you look at the block numbers and zero out the corresponding bit saying the block is free. It's available for use. Okay, is that clear? So essentially you will either use a list or a bitmap. A bitmap is simply a structure, and you can basically scan bitmaps and find free blocks or contiguous sections of blocks very quickly using bit operations. Okay, so a bitmap is a good structure to keep. Now typically the bitmap itself has to be stored on disk. Okay, because if you keep that in memory, if you shut off your machine, that data structure is gone. Okay, so periodically you will keep a copy of it in memory, but periodically as you change this, you have to write it out to disk so that if you reboot, you can read it back from disk into memory. Okay, this data is always persistent. So you cannot keep any file system data structure in memory. It has to be always kept on disk, and you can read it to memory when you need to. If you modify it, you write it back. Okay, so file descriptors, bitmaps, they're all stored on disk. Okay? They're now brought into memory and used in memory as well, so you don't have to do needless disk I/O. So you can read the bitmap when you boot your machine, and as you change parts of it, you write parts of it back. Okay, but you can keep a copy in memory. Okay. There is some small question here saying if you have very large disks, what is the size of the bitmap and how do you optimize it and so on. Here you just have a 2 GB disk, but let's assume it was 2 terabytes of disk. A 2 terabyte disks are lots of sectors, as you can imagine. Okay. And you need 1 bit per sector. So your bitmap itself may be several megabytes or tens of megabytes in size. Okay. So you'll have to keep that entire data structure in kernel memory and keep reading it or writing it back as you modify it. Okay. Now you can of course use other data structures like a linked list allocation for free blocks. Okay, just as free blocks you can throw on a linked list, it doesn't matter. You don't care about the performance of free blocks. What you care about is performance of files. So instead of bitmaps, you can keep them in a linked list organization. Okay, just as we saw a linked list for a file, you can chain all the sectors in a linked list organization if you want to. Okay. So if you, depending on what you use and how you allocate and deallocate space, free block list management will itself have some overhead. When you delete a file, how do you take all the blocks and add them to the free block list? When you want to allocate some space, how do you go and find space in the free block list and allocate to a file? How do you scan it to find the first empty block and so on? Okay. All of these are considerations that you have to keep in mind. Okay, I won't go into too many details here. That's all I want to mention as far as free block lists is concerned. Okay, so we'll end the class here. Okay, so we talked about the first part of file systems, which is how is data stored on disk. Okay. The other part is now that you stored it, if you want to read, how are you going to do it efficiently, assuming magnetic disk? That is coming next time. Okay. It involves scheduling of I/O requests. Okay. We'll see yet another type of scheduling algorithm. We looked at CPU schedulers, we look at disk schedulers. Okay. So For today, let's end it here.